All right, well, good morning. Welcome, everyone. Thank you so much for being here today. I'm Aaron. I'm going to be kind of the host in the background, and we've got Chris Denney, our amazing presenter today. A couple of housekeeping things that I'm going to go through first. Let's see. Okay, Chris, do you still see the opening slide, the PDX slide?
I do, yeah.
Okay, perfect. All right, so PDX is an engineering event that we do, and they're in-person events and webinars, and it's all part of a larger ecosystem that we've put together called the Pipeline Media Lab, where we're creating educational content for engineers. And the goal is to always make it super practical, stuff that you guys and girls can go out and use right away at work. So the Wave is one of those resources. And if you're here, it's probably because you signed up on the Wave, so you probably already know about that. There are all kinds of cool resources there. There are forums, you can connect with mentors, there are articles, all of these webinars get recorded. So if you ever want to watch this webinar again, you can go to the Wave and do so there. We've also got the Being an Engineer podcast, over 300 episodes and going, where we interview engineers, typically senior level engineers or engineering leadership, and learn from them, get some pro tips, and hopefully all of us can apply those in our jobs again to just improve the way that we work. Great way to connect with people. Typically, the people on the show are very approachable and welcome connections. Um, and then finally, we have the Pipeline Media Group newsletter. There's a QR code right here. This is newer, and so you might not know about it, but this is where a variety of things. There's a quick summary of the latest podcast episode. There's also a summary of recent articles that we have on the Wave, and then we announce all of our events there as well. So upcoming webinars, in-person events, things like that, all get announced in the Pipeline Media Group newsletter. So if you haven't already, hit that QR code and go sign up for the newsletter. All right. Um, so getting into today's presentation, Chris's presentation is probably going to be about 20 to 30 minutes, something like that. He welcomes interruptions, and you do all have the ability to unmute yourself. So if you're not speaking or asking a question, please make sure you are muted. But otherwise, if you have something you want to ask and it's time sensitive, you want to interject, feel free to do so. Unmute yourself, ask the question, and Chris can address it in real time. Otherwise, if it's just something you want to make sure gets addressed eventually, put it in the Q&A section, not the chat section, but the Q&A section of this meeting. And I will keep an eye on that section throughout the presentation, and I can bring things up and make sure that they get addressed. So without further ado, I think we'll turn it over to Chris, who is the CTO over at Worthington Assembly. They do PCB manufacturing. He's been in the industry over 20 years and lives and breathes this stuff and is going to be able to teach us a lot today about effective ways to design and manufacture PCBs for you mechanical engineers out there. You'll learn how to communicate effectively with your contract manufacturer or your double E counterparts. And for you double E's out there, you'll get some great pro tips for how to design PCBs that can be manufactured in volume cost effectively. So with that, I will turn it over to Chris Denney.
Thanks, Aaron. I should have asked you this beforehand. Assume we have no way of doing polls here, right? Like
No way
live
of doing
polls.
live
Okay, no
polls,
problem. No
correct.
problem. Just thought I'd ask. Because one of the things I was interested in is getting a gauge for who the audience is. A lot of times when I do these presentations, I do it in person. And then I say, okay, everybody raise your hand if you're such and such or so and so, and get an understanding of who everybody is. But oh, Mike is suggesting that people could click the raise hand button. Let's do that. Let's do that real quick if everybody doesn't mind. If you do PCB design at all, or even just play with it, could you hit the little raise hand button? So we got two people so far. 5 people. Okay, good. All
We
right.
got a bunch.
So that's
Yeah.
pretty diverse. That's good. Okay. So I just like that because then I can kind of gauge how I present this information a little bit differently. So, all right, I'm going to share my screen. And if all goes right, you'll all be looking at each other right now, or looking at Aaron and I for a minute. And then we'll switch to, okay. Now, are we still seeing my presentation controls, Aaron, or are we seeing just my slide?
Just the slide.
Excellent. Perfect. Okay. So I like to title this, I've given this presentation a few times before, but I mix it up each time I give it based on the audience and who I'm speaking with. So I use the same title each time though, because I think it's attention grabbing, but it's also literal. Your manufacturer is stupid, help them. In other words, you know, we don't always know as much as people think we might know. So briefly, I know Aaron gave an introduction for myself, but I'm the CTO for a company called Worthington Assembly. We're a contract manufacturer, small business. We're about 40 employees here, but we are partnered with a company called Circuit Hub. Now, this is has a better brand recognition for a lot of people who do any kind of circuit board design. An easy way to explain who Circuit Hub is sort of like the Proto Labs type business model, but for circuit board assembly. It's an easy way to think of it, especially for you mechanical engineers out there. You're probably familiar with Proto Labs. They're a sister company to ours, and I'm very, very interested in their success. So I kind of work 2 roles, both for Worthington and for Circuit Hub. And also have a podcast called the Pick Place Podcast, which maybe perhaps some of you know me from already, but we talk about everything I'm going to talk about today is more or less fed into the podcast and vice versa. A lot of similar content. If you've listened to the episodes before, that some of this might sound redundant, and if you haven't, hopefully it whets your appetite to listen to some more of it. But a lot of you might know me from episode 50 of Aaron's podcast. That was a great conversation. I really enjoyed it. We should probably do it again, Aaron, sometime. Have an updated round 2.
Round 2.
All right.
All
So
right. Stay tuned.
yeah. So your manufacturer is stupid, but it's largely because we have to act stupid, right? We have to prevent ourselves from making certain assumptions about what it is that you're trying to achieve about your design work. And a lot of this information I'm going to be presenting today is very, very practical. It is very much not at a high level. Like I like to take particular problems that we deal with, highlight them, and show solutions to them. I could do this for 100 different topics, of course, but we're just going to hit on the biggest ones today. Yeah, so excuse me. I don't have all my notes that I normally have, so I might be making a mistake in some of my slide presentations, but I'll do my very best here. But yeah, we have to play dumb, and most of this presentation is going to be about new product introduction. In other words, you know, these are helpful. This is helpful information for long-term production as well, a recurring production type work. But it really, the bang for the buck of this information is going to be for new product introduction. It still becomes, like I said, it still becomes valuable for long-term production, but it's really good for new product introduction. And that's because if information about your design is unclear, things are going to slow down. There's going to be stoppages, there's going to be issues. We try to catch as much ahead of time as we can, but you can't always catch everything. Now, a lot of times, if you're engineers, perhaps you know this already, but a lot of times the argument I hear from people is, well, yeah, but don't just machines build everything? And it's true, yeah, machines do build things. But at the end of the day, it's really the humans that are using the machines, that are programming the machines to build things. And because pick and place machines are so freaking cool, I just wanted to show a video. Hopefully the video plays well over Teams. Aaron, stop me if this video doesn't show good. So this is our pick and place machine, one of them. We have a few. And they are crazy, crazy fast. Crazy fast. That's just a small sampling of it. But in order to get those machines to do that work, you got to start by teaching the machines what to do, right? This is older software. We don't use this software anymore, but this is a screenshot from older software. This is the interface that a engineer in our company is going to look at to prepare the machine for that operation you just saw. So super high tech, super awesome, cool machines are doing all this work, but they're being taught by people how to do this work. And there's all kinds of information those people need in order to program them properly. And then at the end of the day, sometimes you see a person's fingers here. Oftentimes, it is literally just a person putting a part into a circuit board to get this work done. So there's sort of two types of technology when it comes to circuit board assembly. You have surface mount, that's where parts sit on the surface of the board, and that large aluminum capacitor there is an example of a surface mount component sitting on the surface of the board. But then you have through-hole components, and you see the pins of this connector going through the board. And those through-hole components, unless you're building tens of thousands of something, and even then, probably not, you're probably still going to be building this by hand. You really got to be pushing tens of thousands per month before you can even think about automating these types of components with machinery. But even still, it's humans doing the work, right? It is people looking under microscopes, people looking at your boards. They're doing all the actual work. I highlight this because it's important to keep this in mind when you're doing design. I remember talking to a software engineer, and he used this phrase that I loved. He called it having sympathy for the machine when he's writing code. And it was his way of saying, yeah, I could write the code to execute a certain way, whatever, and get the job done. But I know I'm going to take up X number of more CPU cycles to do that, and it's going to hog this much more RAM. He goes, I like to have sympathy for the machine. I like to make it easy for the machine to do the work. And I think if we can have sympathy for Intel, we can have sympathy for the humans on the factory floor that are doing the work and giving them all the information that they need so that it's as smooth and easy as possible. The analogy I like to use is it should feel like riding a bike downhill, like a gradual slope downhill. If everything's going right, it should be easy and comfortable. You're still accomplishing, you're still doing a little bit of work, you're still pedaling, but you have everything you need to get the work done. So I'm going to talk about 5 sort of tent pole problems that a lot of times we experience when we're doing new product introduction. And like I said earlier, these apply to larger volume production as well. But the identifying the polarity of components, those of you who might not be familiar with electronics manufacturing, a lot of components can fit in multiple directions. In other words, they can fit at 0 degrees, 90 degrees, 180 degrees, and so on. But they don't function in the wrong orientation. They need to be in the correct orientation. So a lot of work goes into that. So we'll talk about that. Let's talk about silkscreen legibility. These are the characters that are printed on the circuit board. They're often in white text, you'll see. Panelization. This is a little inside baseball of what we have to do, but how your design can make panelization a little bit easier. Component size consistency. This is a new one I've started to include in my discussions because now this is becoming much more of an issue than it used to be, and we'll get into depth about component size consistency. And I'm going to close with a hot topic. You are not Apple. Great if you are, but most of us are not Apple, and we'll talk about that and what I mean by that. So we'll start by identifying the polarity of components, and this really is the number one thing that slows things down for us. If we can't figure out the way that this component is supposed to go on your board, we're going to have problems. So we're talking about LEDs, diodes, ICs, these are the sort of the smarts, so to speak, of your design, and figuring out what way that it needs to go on a board. Now, I've got some good, bad, and ugly design references here that I'm going to be showing off. So this transformer, it's a very tiny transformer, L8 in this particular area. If you look at, can you see my mouse? I wonder, Aaron, if you can see my mouse. Are you able to see that in the presentation or no?
Yes. Yep.
Okay, excellent. So I'm highlighting this region here, and you'll see there's this little ellipse, right? There's this little bit of information here that's trying to tell us that pin 1 of this inductor or transformer here is supposed to go on this pad. But you'll notice, you got a lot of noise in the way. You got a lot of stuff that's making it difficult for us to see that. And what's worse is once you actually put the component on the board, so that previous slide was the drawing of the board. This is an actual picture of the board. Now that component is completely obscuring the polarity of what direction that's supposed to go on. So when a human is looking at this, they can't tell if it's been populated correctly or not. So it slows things down, right? Here's another example. This is very common QFP. These are used on all kinds of circuit boards. You have a very clear indicator. Now it's not obscured by any other information. However, once you actually put the part on the board, again, that polarity information disappears. How do you know that that's been populated correctly unless you're looking at a drawing? Because the nice thing is with circuit board design is we have full control over making it obvious what direction things are supposed to go in. It's very common to put like a little bit of a slash in the corner here. That's a common way, but again, that's going to get covered. What we love to see and what every manufacturer loves to see, when possible, if you can make it fit, is to put that indicator on the outside of it. Because then when the part gets put on top of the location, it's not obscuring the polarity any longer. Another popular way is just by kind of like putting a long line along the pin one. That's a helpful thing. Or, you know, having a cutout like this one where, you know, you see the two brackets on each side of these three corners, but then over here, you're missing one of it. And that is a clear indicator that it has polarity. This is another example, just putting a line in here at an angle. But all these are very, very visible to the team when they're building things to make sure that everything was done properly. Because weird mistakes happen.
It looks like you're referencing only silk layers. Do manufacturers not look at assembly layers as well? Because the information could be displayed completely differently.
Define for me, if you will, what you mean by an assembly layer. And thank you for asking the question. I appreciate it.
Okay, well, a silk layer is a layer that is printed on silk in the PCB.
Definitely.
An assembly
That's right.
layer is literally just a guide for assembly.
That's right. So exactly. So we will reference that. So I'll call that a drawing, an assembly layer. We will absolutely reference that. And it's helpful to reference that. But you need to have that in front of you. The beautiful thing about silkscreen and what I'm about to go in here, this is sort of like a shortcut, if you will. Rather than jumping over to a computer or having a paper drawing in front of you to verify that you did it properly, you can look at the board itself. The board itself can be your guide. But absolutely, we look at those assembly drawings, no question about it. And in fact, a lot of these boards that we're getting nowadays are so small now and so densely populated, we're telling a lot of our customers, eliminate silkscreen altogether. Please do not put silkscreen on the board because it has adverse effects to applying solder paste, which I don't really get into in this presentation, but depending on how small these components are, it can have an impact on the deposition of solder paste using a stencil printer. So we're telling a lot of customers now to eliminate silkscreen altogether. So another thing that we like to see, as you see in this slide here, sorry, did you have another question, a follow-up question on the assembly drawing before I move on?
Excuse me, I thought you were talking about when the programmers were programming the pick and place, and I assumed they would always have the assembly layer in front of them to program the machine.
They do. They absolutely do. I will say if your silk screen is clear, they're not going to look at the drawing. It's much easier because, you know, we'll have triple monitors and everything. And if they're in the one interface to program the pick and place machine, they're going to look at your silk screen because it's much, much faster. And so it's going to save them time. But if it's not clear, they absolutely will look at the drawing. No doubt about it. But then weird things happen on the manufacturing floor. You might switch from a tape and reeled component to a tray component, right? That's not uncommon. Maybe you couldn't buy enough of the parts in one type of packaging, so you have to switch a type of packaging. And now on the fly, on the line, you have to re-verify that it was done properly. And yes, we will have drawings available to the team, but if it was on the silk layer, it's just going to be faster. It's just shortcuts, right? It's a quick thing to do. I will say though, if you take your time and you put it in the drawing, that will always be helpful. Rather than take, 10 seconds to find the polarity of a component, it'll take 60 seconds, but at least we won't interrupt the line. We'll still keep running. We'll still keep operating. So yeah, please please do a good job with those drawings. We appreciate it. But another idea, and one of the things we love to see when possible, is actually changing the shape of the copper. So in this case, this is an example of where your pin 1 has these nice sharp corners, and then all the other pins have kind of rounded corners. If you can get away with that in your design, that's a really helpful indicator, and it leaves no question which one of these is the pin 1 indicator. We're really love to see that. And then if you use some combination of it, that's great too. You have the long line with the square. We're big fans of when engineers do this for us. There's no question about it that it's been done properly, whether or not you're programming the machine, verifying on the assembly line, or an inspection before you go to ship. If we see that square indicator, that is a huge help for us. Just some more examples of how it can be done and how it can really just emphasize the correct pin 1. LED orientation. So this is an example of where a drawing can be done properly. So in this case, maybe we're looking at a schematic, and the LED has to go down in a specific direction, only allows voltage to go one way. What we see, I would say 9 times out of 10, is the LED is labeled as pin 1 and pin 2. What every manufacturer cares about is the cathode, because almost all LEDs are marked in some way to identify physically. The LED itself is somehow physically identifying the cathode of the LED, whether it's like a line printed on the LED or some kind of cutout. Sometimes I've seen dots poked in the actual substrate, like a physical indentation on them. What we're always looking for is the cathode. So this is oftentimes what we see, pin 1 and 2, but we don't really know is whether or not 1 or 2 is the cathode. I mean, you can read the schematic, but not everybody is always very comfortable reading the schematic. What we love to see is when an A and a C is used rather than a 1 and a 2, because oftentimes when you look at the data sheet, it might say 1 and 2, it can say A and C. Either way, we're looking for C. We want to know where the cathode is. And then if you label your actual footprint with an A and a C instead of just 1 and 2, then it's crystal clear, because what is the square, the 1, or the anode? Is the circle the 1? See, when you use a C, there's no question about it. Cathode, this is where I want my cathode to go. And that shortcuts so many different things. And then if you combine that with a positive and negative indicator, that's a huge help for us. You would be shocked, I think, to know how much time we spend on LED orientation. It's absurd. It's the kind of thing that you can program into a machine ahead of time, no doubt, but you have to verify that all these various inputs that went into getting that machine to run were all done properly. So at the end of the day, you still have to look at how did that machine place that LED on that board. And you have to reference that back to the data sheet. And oftentimes we'll even light up that LED. We'll hit it with a multimeter to verify that the LED lit up in the correct orientation. And then you just can't believe how much work goes into getting this right. Another silkscreen indicator where you have that boxed in, that's great. That tells us it's the cathode. That tells us that pin 1 is the cathode in this case, because sometimes you'll see pin 2 is the cathode. But if you use a C, there's no question about it. There's absolutely no question if you're using a C, what direction it's supposed to be. Sometimes very small LEDs, we'll see customers will actually put a little schematic symbol inside the 2 pads to show us the orientation. That's helpful as well. These are all just helpful tips. You can use any combination of these things to help us get it right. And again, these are all we're just looking at your data in this case, right? We're just looking at the physical, or not physical, the virtual drawing, so to speak, of how you've designed your board. And if you include that A and C, it is a huge, huge help. So basically, just a quick summary: using a square pad to indicate pin 1 for ICs is huge. Using a plus and minus on your silk screen is big, but really the big thing we love to see is a letter C. That just makes it crystal clear for everybody, both in your schematic drawing and in your footprint. Any questions about that before I move on? I'm happy to, I appreciate you interrupting don't be afraid to interrupt me at any point. I'm really comfortable talking about this stuff, but any questions about what I covered so far?
I
Got
put a
another.
question in the Q&A.
Yeah, thank you. I was just about to read that. So we got RGB LEDs often have a common pin that is not pin 1. How do you
Yep.
suggest making those clear?
Yeah, so we'll see the pins labeled RGB. That's oftentimes what we see. If you label the pins RGB, that's clear to us because then we can look at the data sheet and we can match that up to the physical LED. Those are trickier, no doubt about it. Those are trickier. But if you label them with the actual letter rather than 1, 2, 3, 4 of what they're supposed to go to, that's a big help. Yeah.
Okay. Pardon me.
By all means.
Labeling them in silk, because about 10 minutes ago you said eliminate as much silk as possible.
Eliminate as much silk as possible if you have a very dense board. I don't get into all the specifics of why we want to eliminate silkscreen for very dense boards. I would say if you have the real estate, use the silkscreen. If you have the real estate. The trouble is we're building a lot of very tiny devices now. We're building a lot of like wearables and stuff like that. You're out of real estate and you don't have anywhere to put it. And in that case, especially when you get into the biggest reason we want to see the elimination of silkscreen is for specific locations that use extremely fine pitch devices. So you're talking 0.4 millimeter pitch from lead to lead and smaller. We like to see no silkscreen nearby those because, believe it or not, as thin as that silkscreen is, it actually acts as a bit of a bridge, and it's pushing up on the stencil and not allowing the solder paste to get printed properly. It's super thin, but it's thick enough to mess up those really fine pitch devices. But if you have the real estate, use as much silkscreen as possible. If you don't, label your schematic and your footprint RGB or common or whatever, give it text is my point rather than 1, 2, 3, 4. Yeah. Before I move on, anything else? No. All right. We'll go into legibility of silkscreen. More discussion on silkscreen. So this is a highly legible board. I'm a little biased because it's my design, but I take a lot of pride and a lot of time into getting the silkscreen as legible and clear as possible. And a lot of times when we talk about, especially you mechanical engineers out there, all about the minimums of your tightest tolerances and how small can I make this and what's the size of my inside radius and blah blah blah. We talk a lot about minimums, right? And rarely do we talk about maximums. But the thing that I see not enough of in our industry, in electronics design and manufacturing, that I see a ton of in the mechanical design, in mechanical, machining and manufacturing, is you guys have these preferences or recommended sizes of things, right? And I think it's fun to call these the cozy sizes, right? You want it to be no presentation is complete without a cat meme. I had to throw a cat meme in here somewhere. It's the internet after all. But the preferred sizes of things. So what I want to get out there, and I've been proselytizing this, so to speak, this preferred size, this cozy size of silkscreen. This is the size of text where it's pretty small. So if you don't have a lot of real estate, you can still use it. It's not these ginormous letters and numbers, but it's still highly printable, very easy for the PCB fab to put down, and very easy for the humans who are building your boards to read. So, and I tried to make it as easy as possible. And this is what I've been using, and I've been recommending to my customers for a decade now, is just go with 1 millimeter. All right, just go with 1 millimeter high, go with 1 millimeter wide. And I wish I could make it easier, but about 0.18 millimeters in the line width itself. You can do 0.2 if you want, but this is the size that I use for all my designs. And I've been telling all my customers to use for their designs. And it's great because it's small enough, like I said, to fit in most locations. And it's very easy to print. It's very easy to put down with old school silk deposition processes using an actual screen. So these can be screened very easily as opposed to, I'm drawing a blank. This is what happens when I don't have my notes in front of me. There's a new technology for putting silkscreen down. Well, new, it's been out for a long time now. It's like, it's sort of like an inkjet printer. And those can put down much finer lines. They can put down much smaller text. However, they're much slower. They're not as quick as the old school silk screening process. By using the 1 millimeter by 1 millimeter with a line width of 0.18, these will print every time with a silk screen process and everybody will be happy. So you get these nice, crisp, clear, visible, easy to read text. Please don't do this. This is a bad example. This is very difficult to read. You can
Chris,
see.
can I interject real quick here?
Please, yes.
Do you care about rasterized versus true type fonts in your reference text?
We don't. Nope. We do not. If you wanna use Comic Sans, go for it. But I will say, when I do everything, I use. I think you're referring to rasterized. I think I would refer to that as vector. Would that be a synonym for that?
I'm gonna leave that to David. This is Dave Iverson's question.
Yeah, definitely.
Yeah. So I always use vector. That seems to be the preference of the industry. I don't say I could speak with a lot of confidence as to why that is the case. I suspect vector has consistent line widths, maybe. That's honestly just a guess. But yeah, we rasterized or vector is what we go with for everything. I think
is the technology that the manufacturer is going to use, is that like a question I should ask before I send over? Like, is it going to be a silk or printed?
That's probably a question I would ask if I'm pushing outside the boundary of the sort of cozy text, as I like to call it, the preferred. If you're pushing it harder, then ask, are you gonna print or use silk screening? I think if you ask your vendor, they're probably going to tell you both. Most PCB fabs are going to have both technologies. They're going to prefer silk screening because it's much faster and much cheaper for them. But you might present something to them and say, hey, what would you use in this case? Would you use inkjet? I don't think they call it inkjet, but basically, would you use inkjet or would you use silk screening or screen printing? Excuse me. Would you use screen printing? And I want to say most shops are going to have both. The smaller shops are just going to have screen printing, but bigger shops
I use PCBWay and Macrofab quite often, and Macrofab nearly always does printed, and PCBWay nearly always, or excuse me, opposite. PCBWay almost always does printed, and Macrofab almost always does silk.
Yep. Yeah, not surprised. Yeah, I guarantee they have both technologies. PCBWay, they probably just, I'm guessing, like, and shops like PCBWay, JLC, they're probably just standardizing into one process, especially for small volume. They're just going to fit you in the same process as everybody else. If you're only ordering some prototypes, 10 of this, 20 of that. When you get into the thousands, all of a sudden the cost difference between printing versus screen printing gets significant, and they're going to want to save time and go with screen printing. Screen printing is less automatable than jetting, so are they going to go to jetting? They might. Hard to say, really. But yeah, most shops will have both, so I appreciate that perspective. This is a bad example, and we've been looking at this for a while now. Look at how much is covered here. Look at all these indicators are all covered here. These are all covered by the vias here. This is I asked for permission to use this. This engineer has gotten much better. But when I first saw this, I just thought, oh man, we're going to have all kinds of issues. There's so much I could go into here, but we're just going to focus on silkscreen for this one. Yeah, you can just see how like the C is covered over here. The 2 is covered over here. This, whatever came before the 29 is covered here. This is rough. This is big UG, big UG. Now, there is something you could do about this. If for whatever reason, aside from actually moving these silkscreen indicators around so that they're legible, you can plug these vias. So notice you have all these holes drilled. And look, we did our best. We tried to move things around. It was a C here on that 29. If I go back, yes, see the 29. See how we pushed it down? We pushed that down to make it easier for us to see. We'll make small changes like that sometimes. And look at this. This is not the point of the discussion. We're talking about silkscreen. Look, this looks like a giant solder bridge, but if you look at the design, there's all copper there. So that's all intentional. This freaks people out. I guarantee the inspection team is going to go nuts looking at this because they don't want to see that, and yet it's intentional. Anyway, sorry, I digress from the point I'm trying to make here. But what you can do is you can plug these vias. So if you notice back here, these vias, these holes are all exposed. The copper is exposed here. The holes are open, and nothing can sit on them. Imagine if you tried to screen print into that, it would all just fall through. If your design is okay with that, we recommend you plug these vias. In other words, they'll be filled with like an epoxy, and then they'll be plated over, oftentimes plated over, not always plated over, or they'll at least be covered with solder mask. So now you can print the silkscreen right on top of it. So you can actually see the complete line of the 5 there. You can see the C there, and you can see it's printed right over that via. Not all designs allow you to do filled vias. I know there are definitely applications where you don't want to fill your vias. There's some high reliability stuff. There's, but oftentimes if you can get away with it, we do like to see plugged vias, or sometimes it's called tented vias. And then you could literally print your silkscreen right over it. But anyway, making those indicators as good as possible. We really do appreciate that. Yeah, there's a blown up view there of the 5 and the C, and you can see how the silkscreen actually does get printed and stays legible there. So 1x1 characters with a 0.18 millimeter line width. It's what I've been using for years. It's what I've been telling customers to use, and it's starting to get pretty widely adopted now as kind of the de facto what to go with, at least among the designs we're starting to see. Yeah, tent those vias, plug those vias if you can. Before I move on to the next topic, any other questions here?
Yes, I have a question. So if you were working with a young engineer and they just came from something like KiCad or Fritzing, and they gave you something that looked like the previous PCB,
yeah,
that you wanted to smack yourself on the forehead, how would you gently coach them to follow best practices?
Yeah. So you're saying me as the manufacturer, or you as their boss?
Both.
Okay.
Because they'll just send it to PCBWay or JLC PCB, and they'll get whatever they sent. So
yeah. So a lot of times we will end up just building it, and we will oftentimes send back feedback like, hey, you might want to consider tenting these vias and making the silkscreen more legible. It's tricky, right? It depends on the relationship with the customer. If it's a junior engineer, I'll give an example. We had, I'll get into his design later on here, but this guy, Sam, who we worked with early on, it was like, Sam, do you want feedback or do you not want feedback? Like, are you interested to know how to make this easier? I've almost never heard a customer say no. They always want some bit of feedback. And so we'll share with them. So I have actually put together it's just my own personal system for providing feedback. I have a process and a system I follow where I'll take screenshots and I will write up the challenges we have with this particular design in this region, change this about the silkscreen, change that about the vias, and I'll provide that feedback in like a formalized way. And so it's a little less like picking on them. It's more kind of formal. This is just the reality of it, right? Very practical approach to what we're struggling with. And I have spent like some 30-minute sessions with them and doing some screen sharing and walking them through, no, don't do this. Yes, do that. So that's just some personal experience of what I've done in the past. And then as a boss, I would tell them, try building it yourself. I can't believe the number of people that I've talked to that have provided us great designs, like really great designs, really easy to build, they often built their own boards for a small period of time, or they built their own prototypes and they experience that pain for themselves. And that's really helpful.
Okay, that's good to know. Thank you.
Yeah, of course. There's another hand with the initials GS.
Yep. Graham here. I think one of the things that I've always tried in a bunch of different companies and a lot of different roles is to encourage younger engineers to ask. Because we go to school, we get all this training, we come out, we're engineers, we think we're all fancy and shiny and know everything. But, you know, if we're in the design space, we frequently aren't familiar with all of the things that happened in the manufacturing space. So an old timer, when I first started my career, said, if the only thing that you do is you ask, what did you think of this design, or what do you think of this approach? Then you're always going to get feedback that it helps improve the sophistication of your design and its manufacturability by asking the people who actually are putting it together. And hilariously, I got this advice from an oil field guy, but it's held true in device development, medical device, different types of fabrication. So again, I always take my young engineers and say, you know, when you preempt the situation and you ask for advice, you're always going to get more and more open and more freely fed feedback than if you just go about your job and pretend like you're perfect already.
Totally agree. I couldn't have said it any better. Thank you, Graham. I appreciate that. That's really good. The other thing I like to recommend to people, and this is something I do when I train people here, is I tell them, look at what came before you. Look at other examples, look at other PCBs, look at what everybody else is doing, and pay attention to how yours looks different. And humans are great at pattern recognition. They'll see the differences. Yeah. Thank you. I appreciate that. So I want to make sure I get to the rest of this as we've got 12 or 11:43. So to talk about panelization, this is my friend Sam's design. So this is what the design looks like in KiCad. Which is actually getting pretty powerful. I'm pretty impressed with what they've done with this open source design software. But anyway, I digress. But this is what it looks like when it's actually built. And notice these two overhanging potentiometers. When we panelized this, we didn't realize we had those overhanging potentiometers. So if you've ever been in a circuit board factory before, you'll notice that boards aren't built individually. They're built in panels like this. And a lot of times we'll put frames around them. And we'll oftentimes butt them right up against each other. This is kind of an old panel design. We probably wouldn't have done it this way in the past. But anyway, I digress. My point is, these are the holes here to put those potentiometers, but we've got no room for them because of the way that we panelize them now. So now we're running into a situation where we kind of have to hand solder these things. So it's a real pain in the neck. So this is what the design looked like, and what we're recommending. Let me move on past this here. Less important. You see, here's a dimension. If you can just throw that dimension into silkscreen, that will be a huge red flag for us saying, hey, there's overhanging parts here. And we have to be mindful of that before we go and panelize thousands of these boards. Another big help, and so this is what it looks like. Now you see before and after where it's hanging over the edge. We know there's a great big part that has to go there. You don't have to get elaborate, don't have to go nuts, but if you give us something, it warns us that there's something closer to look at here. 3D models are also very, very helpful. We will reference 3D models, not every time, but oftentimes we'll reference your 3D model. And if we can see that overhang, that's good. We'll even be able to measure it right from that 3D model. Trouble is, there's 3D models and then there's 3D models. So your Gerber data is perfect. Your bombs are nearly perfect. Your 3D models, we've seen the good, the bad, and the ugly when it comes to 3D models, because it's a lot of work to put these together. It depends on the customer. Some of them are better than others, but those are quite helpful to have 3D models. I'm running through this quickly only because we're getting short on time, but that's the gist of it there. Any questions about overhanging parts and panelization? Cool. Well, if there are any more questions, just as we go on here, bring them up. Component size consistency. So we're running into this now where we're getting very large parts next to very small parts. So this diode here, I can't get into the details as to why there's exposed copper here from the solder paste, but you'll notice that this diode has to go here. It's very, very tiny next to this huge connector and these relatively large ICs next to it. And when it gets populated, you can see significant size difference. What we're seeing oftentimes is we have boards with lots of real estate, big, huge components everywhere, and then really, really tiny diodes or really, really tiny resistors, or, you have the real estate for larger parts, but you're not taking advantage of it. You're using really, really small parts. That creates the biggest issue when it comes to stencil printing. So this is like a cross section of what it looks like on a stencil printer, or on a stencil printer. So the green is representing the circuit board. And then the gray, the silver, is representing the cross section of what a stencil might look like. What we're having to do when we see these large components next to really small components like this is we're having to use things called steps. So the way that these are made is super, super cool. I don't quite have time to get into how they're made, but we'll actually thin out the stencil over here for where we need smaller apertures. And then we'll bulk up the stencil over here for where we need more solder paste. But it's not a perfect solution, because once you pack those things with solder paste after the squeegee goes over it, and then you lift up your stencil, come on now, here we go. You lift up your stencil, now it'll get stuck inside some of these apertures if you step it up too far and your apertures aren't large enough. And there are all kinds of complications with all kinds of, let me put it this way, all kinds of things we need to calculate in order to avoid this type of an issue from happening. When possible, using the real estate that's available to you, using the larger components if you can use them, and avoiding the mixed use of very small and very large components makes the assembly process much, much easier. It's not that it cannot be done. There are cases where you just have to do it. Like we have one customer, one of our largest customers, they use, they have these great big huge RAM sockets, right? Well, actually, they're pretty small RAM sockets, but relative to the board, they're huge. They're these huge RAM sockets. And then they have tiny, tiny, tiny little 0201 diodes all over the board for ESD suppression. Their board is extremely dense. They have to use those tiny diodes. And they also need to have RAM sockets for, when they sell their products. Some of the boards get 4 gigs of RAM, some get 8, right? So they need to have these sockets. They can't avoid the fact that they need to mix technology. So I totally get it. I'm not saying that this is an impossible thing to do. I'm just explaining that it makes it harder. It just makes it more difficult. So when you have the real estate, use the larger components. If you have a very dense board, try to stick to all very small components, right? So if you're using a tiny little ESD suppression diode in one area, don't go and use a huge 1206 resistor in another area. Stick to your 0201 resistors or 0402 resistors. Whenever possible, try to move the spectrum of the types of components you're using along the same plane with each other. Don't spread those out as much as you can. I totally get that it's unavoidable at times. This is what it might end up looking like. This is a terrible stencil print where our apertures were, I guess, probably too large in this case, or too thick. The stencil was too thick. We didn't have a good step down. And you see the solder paste is just bridging all over here. It's bridging all over here, but you see much larger components nearby. So we needed the volume to get a sufficient solder joint on those other ones. But this is a tiny little BGA. I think this BGA is like the size of an 0402 or an 0603. It's really, really small, and really difficult to get right. And you can see the height of the silk screen actually is probably part of our issue, is pushing up on that stencil and making it thicker and not allowing us to get a good gasket on the board itself. But yeah, whenever possible, try to keep the consistency of your sizes similar to each other. Any questions about that before I move on? Great. I know everybody's waiting for this one. It's not as exciting as you think. Circuit boards are green. This is my biggest pet peeve. It has become super popular thanks to a fruit company in Cupertino, California, to make your circuit boards black. And believe it or not, black solder mask has a negative impact to the ability to fabricate your boards and assemble your boards. It has a negative impact on both. It looks super, super cool. Believe me, I get it. And as a matter of fact, a lot of times if you're ordering from Circuit Hub, we're going to default it to black because it's sort of just become our default, like kind of like a marketing thing. We just like, oh, they're black circuit boards. They probably came from Circuit Hub. Believe me, it does look super cool, especially with the gold. And all right, I get on with it. Here's the issue. Black circuit boards don't like to reflect light. They're black, right? There are light sensors used in all kinds of automated machines. And these light sensors want to shine a light and see the reflection of the light come back into them. And black just absorbs that light. We have taken the time to make sure that all of our light sensors see black circuit boards because we get so many of them. But even still, we still will struggle seeing black circuit boards at times during assembly. It seems crazy, but this is the truth. And then your solder mask slivers, where you can fit solder masks. This is not a great image, but I just had to find one quick. I stole this from one of our vendors. I forget who it is, but with permission. This is, oh no, you know what this is from? This is from Altium documentation. So it's public information, but the solder mask has to fit between the copper here, right? Believe it or not, when it comes to green, now here I got to reference my notes. Okay. If you're using green solder mask, you can easily get about 2/1000ths sliver. This dimension can easily be 2/1000ths or 2 mils. When it comes to black, you're going to get a much harder time getting down to 2/1000ths. Usually you like to see 4/1000ths. And this is because most of PCB fabrication is done with light. And the light does not like to penetrate black. It's just how colors work, right? So the green has been highly optimized for this UV light exposure process that everybody uses. So circuit boards are green. You're not Apple. And if you are, great, send some business my way. We work for a fruit company, but not too much. Anyway, so those are my 5 tentpole problems that I like to highlight. And I do have a bonus tip. Is there any questions about what I've gone over so far? Just trying to be mindful of our time. Okay, looking pretty good. Briefly, use square pads and make your silk screen very clear. Use 1 millimeter by 1 millimeter characters. Produce 3D models. Those are helpful. We'll use them if you provide nice, consistent 3D models. Try to keep your part sizes consistent and use green solder mask. Here's my bonus tip. Keep SMT parts 3 millimeters from through-hole parts. This is the keep out area of when you're trying to use a selective soldering machine. If you don't do this, we will either need to get special fixturing made, we'll have to hand solder it, we'll have to maybe apply temporary solder mask that we have to peel off after, and so there's a setup time, you got to wait overnight, and sometimes it falls off, and sometimes there's all kinds of complications. If you can keep this recommended distance of 3 millimeters from your next adjacent, so this X dimension here, if you can keep that X dimension to be 3 millimeters, life is good. We're really happy, and we can automate the soldering of your through-hole components. So that's my little bonus tip. I'm trying to get this out there as much as possible for customers. There are so many other things I wanted to go into. This is not even half of all the other things that I could have gone into. I talk a lot about these on the podcast. So if you are a design engineer and would be interested, I recommend you subscribe to the podcast. We talk a lot about all these things. We can go into further detail. I think that's basically it. Yep.
I know we're at the end of the hour, but do you have any advice for calculating pin and paste pad mask openings?
Yeah, my advice is to ask your manufacturer too. So we do that. We will calculate pin and paste openings. We have calculators that we use for that. They're provided by our stencil suppliers. And we will take the size of the pin, the size of the hole, the thickness of the board, the thickness of the stencil, all these things into consideration. It's a pretty big formula to do all the calculations. I will
That
say,
sounds like a process that should be done before layout, though. And if I'm getting it to the manufacturer, my layout's already done. And if I don't have room for the pad opening that they expect or they need, then I'm screwed.
yeah, you kind of are. You're not wrong there. A lot of these USB-C ports, they don't look great when they come out of assembly because we can't pack enough solder paste in them. But there's not much you can really do about your design. But you're right. You know, I don't think I have a great answer for you for how to handle that pre layout, or in other words, before you finish your layout.
Yeah, I've got a board that's got like two parts that have to be through hole, and I don't want to do selective solder because it's a slower process and it's a second process.
That's right.
Right. So if I want to preemptively load that information in my footprint so that when I'm doing the layout, I know that I've got enough room for that. So that's kind of a catch-22.
That's a great point. So I would say in that case, probably reach out to your manufacturer and let them know that you want to do it pin and paste. Hopefully they have experience doing that and they have the calculators already and they can share that with you. It's probably going to be a bit of a collaborative process. It'll probably be a bit of back and forth. Because it's not as straightforward as you might think. There's going to be other considerations that have to go into it, but because the type of paste they're using is going to have an impact on that.
How much what do you call it? Solvent is in it, the volume change after wetting, like all this other kind of stuff is like the meniscus diameter, all this stuff.
Everything. It's a pretty big calculation. You're right. Yeah. So I think that's probably the best thing you can do is let them know ahead of time what you're trying to accomplish. If they come back to you and they're like, what's pin and paste? Maybe find another manufacturer.
Absolutely.
They should be familiar with that already. Yeah. Great question. Any others related to my bonus tip? That was kind of a question about my bonus tip because he wants to avoid selective altogether. Okay. Well, our website, worthingtonassembly.com/best practices. There's some helpful information on there. We have plans to flesh that out a little bit more. We don't have a ton, but I have recommended discrete footprints that you can use that are great. If you have the real estate to use them, awesome. They're really, really solid footprints for discrete components, your 0201s, 0402s, and so on. Again, subscribe to the podcast. We talk a lot about these subjects in the podcast and others, just unrelated things. We get into test, we get into, well, it's for designers. There's a lot of podcasts in our industry that's for our industry, but this podcast I think is one of the few that is industry talking to design, which I don't think there's enough of. So hence why I made it. Let's see. And then I think it's just my contact information. So feel free to screenshot that or whatever you'd like to do. And thanks very much to Sam Feller, the awkward engineer, for letting me use his designs in this presentation. I appreciate that. Email me anytime. I am a prolific emailer. I may not respond right away, but I promise I always do respond at some point. But you can reach out to me on LinkedIn. I'm trying to use that a little bit more. There's a pretty good community out there, people on LinkedIn having really nice discussions there. But yeah, email is a great first step. And I think that's it. Yeah.
All right, Chris, thank you so very much for sharing your valuable time with us today. This is awesome. Lots of super practical advice for all of us about optimizing our PCB manufacturing. If there are any last minute questions, ask them now. Otherwise, if we don't see anything else pop up, we will go ahead and end this, and this recording will be available for time and all eternity in a few days on the Wave, so you can always go back there and watch the presentation or reference different parts of it again. So thank you again to Chris, and thank you everyone for showing up today and being part of this community. We really appreciate it, and we'll see you next time.
Thanks very much, everybody.
Have a good one. Thanks, Chris.
Thank you.
Thank you.
My back is killing me for standing for an hour, so I'm gonna go. Thanks, everybody.
All right. Thanks, Chris. See you
Getting
later.
old, Aaron.
Happens to all of us.
We'll see you.